Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are studying Chapter 5, the thermodynamic processes and cycles, and we are wrapping up our study of heat engines with this video lecture. We're going to very briefly look at the Brayton cycle. Now, the Brayton cycle is in some respects quite similar, but also very different from the Rankine cycle. This is an idealization of a simple gas turbine that was proposed by Brayton in the 1870s. So it's been around a long time, but this is the core of how, say, a jet engine works. They're going to add nozzles and some other fancy things like that, but this is the basic idea. We're going to start by bringing in air from the surroundings. Again, if you're thinking about a jet engine, what that would do, right? It's going to bring air into the device, and it's going to compress that air to a high pressure. It's then going to heat that air up, and the way it's going to do that, right, we're not going to be able to boil it, right? That makes no sense. It's already a gas. And so we're going to run it through a combustion chamber that's going to provide a lot of heat and add that to this. So the air is actually going to be part of that combustion process. We add fuel, a spark, and you got yourself a fire. So the combustion chamber is next, and we're going to be modeling this for this course just simply as heat transfer in. When we take our Thermo 2 class, we'll have an opportunity to look at the energy, exactly what fuel we might be burning and so forth. So we could look at those specifics at a later time. But for now, simply heat transfer is happening there. Now we have this gas that's been compressed to a high pressure. It's got a lot of heat added to it because of this combustion. And now then we're going to take this high energy air, essentially, and run it through our turbine and exhaust it back out to the atmosphere, the surroundings. And we want to be sure that we exhaust it pretty close to the conditions of the surroundings if we can get it there, simply because that's going to optimize our resources. Now, if I were wanting this for, say, jet propulsion or something like that, I'd run it through a nozzle next, and I would do some other things. But this is our basic Brayton cycle. And all throughout here, I have gases. And typically, we model these as if they are an ideal gas, air. The assumptions that we make for studying this is that we start with reversible adiabatic compression. Okay, so this is similar to our pump, except it's not a liquid, so I can't use V delta P. I must use delta H in the analysis. So I've got, that is my first step, compression, reversibly and adiabatically. Next, I'm going to do heating. Again, I'm going to assume it's isobaric, constant pressure. And I'm just going to model this as heat transfer into a final temperature, whatever that combustion temperature might be. Next, we're going to do reversible adiabatic expansion. That's our turbine, okay? So that's going to be work, but it's adiabatic. We don't want to waste any of that energy. And then finally, that last step where we exhaust the gas to the air and then bring in fresh air, we're just going to replace that with reversible isobaric cooling. It is isobaric. I guess it's kind of reversible, if you're not counting which molecules are where. But anyway, so that's kind of a magic step there. There's no equipment associated with it, but we are going to have waste energy. If we're not dealing with kinetic or potential energy, then every step is going to be modeled using Q plus W equals HE minus HI. There's one stream in and out. And I can do these all using ideal gases. Now, as chemical engineers, we don't have a lot of call to do this. However, I am going to remind you that at the end of Chapter 4, we looked at polytropic processes. These reversible and adiabatic expansion and compression steps are those polytropic processes where N is equal to gamma, the ratio of C sub P to C sub V. So therefore, in the analysis to calculate the work, that's some really useful equipment or equations at that point. So you'll want to go back and look at that if you're ever called upon to analyze a Brayton cycle. So this was a very quick look at this, but I just wanted to show you something different from the Rankine cycles that we've been doing. We're next going to be looking at refrigeration cycles. Thank you very much for your time.